Hi, I'm Russ Klein. I'm a program director with Mentor Graphics Embedded Software Division, and I'm going to show you a little bit about our system analysis tool, System Analyzer. So System Analyzer is an Eclipse plugin, and its primary job is to let you go into your system and look both at the applications and the system level and figure out what's going on with your programs. What we're going to do is first open a project, a System Analyzer project, and we're going to call it S1 for Sudoku first implementation. Then what we'll do is import some data into it, some System Analyzer trace data, and import LTT and G1. At this point, what we'll do is open up the system overview. And the system overview will show us we've got cores 0 through 8, or 0 through 7, and this will show us exactly what they're doing. We can zoom in here a little bit. The blue spaces are actively working on a user process. The gray spaces are idle. If we zoom in yet further, we can see things such as system calls, traps, soft IRQs, busy. Let's take a look at the overview. We can also see the interrupt lines, the soft IRQs, traps, and below this we see all the different processes. What we're really interested in looking at is our Sudoku threads. Now, the Sudoku program that we've got running is processing 5 by 5 Sudoku, so there are a total of 25 digits. And the main thread will spawn off one worker thread for each of the digits. So here we have the worker threads being created. What we see is that 4 threads get created. We have a little bit of time, and then 3 more threads, and then yet 3 more threads. One of the things that we can do is open up a filter, and from the filter we can extract the kernel migrate task field, and we can say when the process ID equals 10264, what we want to see is a step function, and we want to see the kernel migrate task, the field destination CPU. What this will give us is a step function that will show us which CPU the main thread, the main Sudoku thread, is running on. If I drop that cursor back in there, we can see he's on core 7, he's on core 2, back on core 7, core 1, core 1, core 3. So what's happening is our main thread is unable to launch all of the worker threads in succession because it is being swapped out and preempted by the worker threads that it's creating. So what we did was we rewrote the program so that there was a pthread wait. And we'll put this into a second project where we can show you the result of this. So this was our second implementation. So what we did is we had all the worker threads launch and then drop into an IO wait state by putting a pthread barrier wait at the entry point to the function. So the worker threads would come to life and suspend themselves, and that would ensure that the main thread was able to launch all 25 worker threads before getting swapped out by any of the workers. And this would allow all the threads to get launched. And as a result, we expect to see much higher core utilization than we have in this case. So the Linux operating system has basically been optimized so that related threads are clustered on common cores, and it does this to minimize the communication costs between them. But in this case, we've got individual threads that aren't communicating with each other, so we actually can be spread out amongst all of the cores. So the situation we have here is suboptimal. So what we did was we rewrote the algorithm using Affinity, and the Affinity allows us to identify which core will be running which thread. So now we can see that most of the time we've got 7 concurrent threads. Here through this region we get 8 concurrent threads working. Now what's going on is each of the threads has a fixed amount of work. The work done on the puzzle is actually going to vary by number, and we can tighten up this ending by creating a work queue. The work queue will allow each of the 8 threads so that when it finishes its pre-assigned work, if there's any work left to be done, it can offload the work from another core onto itself, and that'll even out the total time that each core is working between runs, and that should improve the overall core utilization. Going from the initial first implementation that looked like this to the second implementation, we actually ended up running about 50% slower. In this implementation, we ended up running about 6 times faster than the single-threaded version. So we're doing pretty good now. We can do a little bit better. So this is our 4th implementation. We'll take a look at that. So here we have the 4th implementation of the Sudoku puzzle. Here we're running a work queue with assigned affinity for each of the 8 worker threads. And we can see that indeed we've got the threads ending fairly evenly, and we're getting very good core utilization. So here we've got all 8 CPUs concurrently working, all 8 worker threads running. We go into CPU wait for the main thread, but that's fine because all of our worker threads have been launched, and all the worker threads end at about the same time. This Sudoku implementation runs about 7.2 times faster than the original single-threaded, single-core implementation. So while we don't get a full 8x running on 8 cores, we're not that far behind. System Analyzer was able to show us where we could where we could identify the unused cores and be able to rearrange our program a little bit to be able to take better advantage of it. So System Analyzer gives us the ability to measure what's going on the system and do calculations on that data and visualize that data to be able to figure out what's going on with our program and to be able to improve it.